When capacitors are connected in parallel, their capacitances are added together. The formula for the total capacitance of capacitors in parallel is C total equals CON plus C2 plus and so on plus Cn, where C total is the total capacitance and CON, C2 through Cn are the capacitances of the individual capacitors. Given two 15 microfarad capacitors connected in parallel, the total capacitance is C total equals 15 microfarads plus 15 microfarads, which equals 30 microfarads. When capacitors are connected in series, the reciprocal of their capacitances are added together. The formula for the total capacitance of capacitors in series is 1 divided by C total equals 1 divided by CON plus 1 divided by C2 plus and so on plus 1 divided by Cn. Alternatively, C total equals 1 divided by the quantity 1 divided by CON plus 1 divided by C2 plus and so on plus 1 divided by Cn, where C total is the total capacitance and CON, C2 through Cn are the capacitances of the individual capacitors. Understanding capacitance is fundamental to electronics. Capacitance is the ability of a component or circuit to collect and store energy in the form of an electrical charge. Capacitors are devices designed to add capacitance to a circuit. They are used in a variety of applications such as energy storage, filtering, and signal coupling. The unit of capacitance is the farad, but in practice, microfarads are more commonly used. A capacitor consists of two conductive plates separated by an insulating material called a dielectric. When a voltage is applied across the plates, an electric field forms in the dielectric, causing charge to accumulate in the plates. The amount of charge stored is proportional to the voltage and the capacitance of the device. The behavior of capacitors in circuits depends on how they are connected. Capacitors can be connected in parallel or in series, each resulting in a different equivalent capacitance. Firstly, let's consider capacitors in parallel. When capacitors are connected in parallel, they share the same voltage across their terminals. This means the total charge stored is the sum of the charges stored on each individual capacitor. Since capacitance is defined as charge divided by voltage, the total capacitance of parallel capacitors is simply the sum of their individual capacitances. This can be expressed mathematically as C total equals CON plus C2 plus C3 and so on, where C total is the total equivalent capacitance and CON, C2, C3, and so on are the individual capacitances of each capacitor. For example, if you have three capacitors with values of 10 microfarads, 20 microfarads, and 30 microfarads connected in parallel, the total capacitance would be 10 plus 20 plus 30 equals 60 microfarads. Secondly, let's consider capacitors in series. When capacitors are connected in series, they have the same charge flowing through them. However, the voltage across each capacitor is different and depends on its capacitance. The total voltage across the series combination is the sum of the individual voltages across each capacitor. To find the total capacitance of capacitors in series, you need to use the reciprocal formula. This is because the total capacitance is less than the smallest individual capacitance in the series. The formula is 1 divided by C total equals 1 divided by CON plus 1 divided by C2 plus 1 divided by C3 and so on. To find C total, you need to take the reciprocal of the sum of the reciprocals of the individual capacitances. For example, if you have two capacitors with values of 4 microfarads and 6 microfarads connected in series, you would first find the reciprocals, which are 0.25 and 0.1667 respectively. Then you add these reciprocals together to get 0.4167. Finally, take the reciprocal of 0.4167 to get approximately 2.4 microfarads. Therefore, the total capacitance of the two capacitors in series is 2.4 microfarads. It is important to remember these formulas and understand how capacitors behave in parallel and series configurations. This knowledge is essential for designing and analyzing electronic circuits that use capacitors. The total capacitance calculation depends on how the capacitors are connected, whether in parallel or series. In parallel connections, the total capacitance is the sum of individual capacitances, while in series connections, the reciprocal of the total capacitance is the sum of the reciprocals of individual capacitances. These principles are fundamental to circuit analysis and design. Capacitors play a crucial role in electronic circuits, influencing their behavior in various applications. In filter circuits, capacitors block DC signals while allowing AC signals to pass through. This is used in audio equipment to remove unwanted DC offsets and noise from audio signals. In power supplies, capacitors smooth out voltage fluctuations, providing a stable DC voltage to electronic components. They act as reservoirs of charge, storing energy during periods of high voltage and releasing it during periods of low voltage. In timing circuits, capacitors are used to create delays and control the timing of events. The time it takes for a capacitor to charge or discharge is determined by its capacitance and the resistance in the circuit. This property is used in timers, oscillators, and other timing-based circuits. Capacitors are also used in energy storage applications such as in electric vehicles and hybrid vehicles. Large capacitors can store significant amounts of energy, providing power to electric motors and other high-power devices. The amount of energy stored in a capacitor is proportional to its capacitance and the square of the voltage across it. In summary, capacitors are versatile components with a wide range of applications in electronic circuits. Understanding their behavior in parallel and series configurations is essential for designing and analyzing these circuits. From filter circuits to power supplies to timing circuits, capacitors play a crucial role in shaping the behavior of electronic systems. Capacitance is measured in farads, symbol F, which is a relatively large unit. More commonly, capacitance is expressed in microfarads, 1/1,000,000 of a farad, nanofarads, 1/1000,000,000 of a farad, or picofarads, 1/1,000,000,000 of a farad. A capacitor stores electrical energy in an electric field. It is a passive electronic component with two terminals. The effect of a capacitor is known as capacitance. While some capacitance exists between any two electrical conductors in proximity in a circuit, a capacitor is a component designed to add capacitance to a circuit. The capacitor was originally known as a condenser or condensator. This name and its cognates are still widely used in many languages, but rarely in English. The physical form and construction of practical capacitors vary widely, and many types of capacitor are available commercially. Most contain at least two electrical conductors, often in the form of metallic plates or surfaces separated by a dielectric medium. A conductor may be a foil, thin film, sintered bead of metal, or an electrolyte. The non-conducting dielectric acts to increase the capacitor's charge capacity. Materials commonly used as dielectrics include glass, ceramic, plastic film, paper, mica, and oxide layers. Capacitors are widely used as parts of electrical circuits in many common electrical devices. Unlike a resistor, an ideal capacitor does not dissipate energy, although real capacitors dissipate a small amount due to non-ideal behavior. Capacitors are widely used in electronic circuits to block direct current while allowing alternating current to pass. They are also used to smooth the output of power supplies, store energy, generate time delays, generate oscillating signals, or tune resonant circuits. Capacitors can be connected in parallel to increase the total capacitance or in series to increase the voltage rating of the combination. The behavior of capacitors in circuits is governed by the fundamental relationship between charge, voltage, and capacitance. The charge Q stored on a capacitor is directly proportional to the voltage V across it and the capacitance C of the capacitor. This relationship is expressed by the equation Q equals C times V. The amount of energy E stored in a capacitor is given by the equation E equals 1/2 times C times V squared. This equation shows that the energy stored in a capacitor increases with both capacitance and voltage. Capacitors are used in many different types of electronic circuits. Firstly, filtering circuits. Capacitors are used in filtering circuits to remove unwanted frequencies from a signal. For example, a capacitor can be used to block direct current while allowing alternating current to pass. Secondly, timing circuits. Capacitors are used in timing circuits to create delays or generate oscillations. The time it takes for a capacitor to charge or discharge can be used to control the timing of events in a circuit. Thirdly, energy storage circuits. Capacitors are used in energy storage circuits to store electrical energy for later use. For example, capacitors are used in power supplies to smooth out voltage fluctuations and provide a stable voltage to electronic components. Fourthly, coupling circuits. Capacitors are used in coupling circuits to transfer alternating current signals from one circuit to another. A capacitor can be used to block direct current while allowing the alternating current signal to pass through. The equivalent capacitance of capacitors connected in parallel is simply the sum of the individual capacitances. This is because the voltage across each capacitor is the same and the total charge stored is the sum of the charges stored on each capacitor. The equivalent capacitance of capacitors connected in series is more complicated to calculate. The reciprocal of the equivalent capacitance is equal to the sum of the reciprocals of the individual capacitances. This is because the charge on each capacitor is the same and the total voltage is the sum of the voltages across each capacitor. Capacitors are essential components in a wide variety of electronic circuits, and understanding how they behave is crucial for anyone working with electronics. The ability to calculate total capacitance in series and parallel circuits is a fundamental skill for electronics technicians and engineers. In summary, calculating total capacitance involves different approaches for series and parallel connections. For parallel connections, simply add the individual capacitances. For series connections, use the reciprocal formula to find the total capacitance. Understanding these principles is essential for circuit analysis and design. Capacitors are essential components with a wide range of applications, playing a vital role in electronic systems.